Hey everyone, let's go ahead and do some optimization problems. In all these optimization problems, we're just finding a maximum or minimum value of some function, in which we already know how to do. The kind of new step that is being added on to what we've been doing previously is we're not going to be explicitly told what function we are trying to maximize or minimize, or maybe what interval of interest we are working on. We're going to have to distill all that information from the problem statement. So in this example, we are a contestant on a game show where we are given a 4-foot by 4-foot piece of cardboard, and we are asked to remove some squares from each corner of the cardboard so that when we fold those flaps up, it creates a little open top box, right? And the idea is however much money we can fit in this open top box is the amount of money we will get from the game show, as long as our box holds more than any of the other contestants' boxes. And so our goal here is to figure out what size of a square should we cut out of each corner to have the most money in our box in order to win the game show and get to keep all of that money. So there is a bit of a procedure that we can follow for all these optimization problems. The steps will all kind of have the same general flow to them, but all the details will change for each individual problem. And the first thing I always do for these optimization problems is try to identify my objective. That is, what quantity am I trying to maximize or minimize? What are we trying to optimize here? What we're really trying to create here is the box that holds the most amount of money. So we're trying to find the box with the greatest volume. So our objective here is to maximize the volume of this box. All right, so we need more information than just knowing we want to maximize the volume of the box. There's always also going to be, and this is within the problem statement, some kind of constraint on the situation, making it so we can't make the box just as big as possible, right? And so the constraint in this situation is, well, we have this 4-foot by 4-foot square of cardboard that we are working with. What are we doing with this piece of cardboard? We are cutting a square out of each corner of the piece of cardboard. That'll leave us with these 4 little side flaps. We can then fold those side flaps up and create our little open top box. And so we don't know how large of a square we're going to cut out of each corner. So that is going to be our unknown that we are trying to find. We're trying to find the value of x that makes it so our box holds the most volume possible, because the largest volume possible will correspond to holding the most amount of money in that box. So once we've identified the objective, the thing we're trying to maximize or minimize, and we look at the constraints, we're ready to start putting that information together to actually start constructing some equations that we can work with to find the maximum and minimum values of our, in this case, volume function. And so my third step in this process in general, after finding the objective and the constraints, is write down some equations using the information from our objective step and our constraint step. So our objective is to maximize the volume of a box. And well, the volume of a box is just a product of its length, height, and width. What we don't know, what we are trying to figure out, is the value of x that we have to choose to remove these squares from each corner that makes the volume of this box as big as possible. So we have our equation for the volume, but now we need to rewrite that equation in terms of the thing we have some control over, and that is the value of x. So we have to figure out how to express the length, the height, and the width of our open top box in terms of this unknown variable x. And well, to do that, we just have to think of what our open top box might actually look like. And so remember, we create the open top box by folding these little side flaps up. So the height of our box is going to be the length of that little x value, that side flap. And then what about the length and width of our box? Well, that's just going to be the length and width of each of these side flaps. So if we look at the length of our original box, it was 4 feet wide, but we're going to have to remove a length of x from each side of each length of our box. So the actual length of our box isn't going to be 4 feet anymore. It's going to be 4 minus 2x. And due to the symmetry of the situation, since we start with a square, the width of our box is also going to be 4 minus 2x. And we know the volume of a box is just a product of the 3 dimensions, the length, the height, and the width. We found the length to be 4 minus 2x. We found the height to be x. And we found the width to also be 4 minus 2x. And so now we have our objective function. This is a function we're actually going to try to find the maximum value of. You might want to rewrite it so that it's easier to work with its derivatives and things like that. So basically, if we just expand all 3 of these factors And so now we've taken this kind of complex problem written in this problem statement up here and kind of simplified it to a problem we are more familiar with. Now it's just one of our kind of max-min questions. What is the maximum value of this function? The volume function 16x minus 16x squared plus 4x cubed. But before we actually start trying to find the maximum value of this function, let's think a little bit more about our situation, because there's actually a little bit more of a constraint that we can apply here. If we think about all the different possible values for x, it doesn't make sense for x to be anything less than 0, right? We can't make a negative side cut. That'd be like adding more cardboard to our box, which is definitely against the game show rules. So 0 is like the minimum value for x. What would the maximum value for x be? Is there even a maximum value? Well, it looks like x couldn't actually be more than 2 feet, right? The kind of worst case scenario is if x was 2 feet, then we'd be cutting a 2 foot by 2 foot square out of each corner of our 4 foot by 4 foot box, but that would just take away the entire box. There would be nothing left. So kind of in the extreme situations when x is 0 or 2, we'd be creating a box with no volume. So our actual x value is going to have to be somewhere between 0 and 2. Those are the only x values that make sense for our situation. Our new problem that is really equivalent to our original one is find the maximum value of 16 minus 16x squared plus 4x cubed on the interval from 0 to 2. So let's go ahead and actually find the maximum value of this function in the space over here. We'll have to get rid of our problem statement. But now we can go ahead and optimize our function. All right, so now to optimize our function to actually find the maximum value of our volume function and the x value that corresponds to that, well, we're going to have to just go through our process using either like that first or second derivative test, or in this case, maybe that extreme value theorem. But they all start with finding the critical numbers. And remember, to find the critical numbers, we have to look where our derivative is 0 or undefined. So let's find our derivative to get started with. If we differentiate our function, we end up with 16 minus 32x plus 12x squared. And so if we want to find the critical numbers, we got to set this derivative equal to 0. Right, this derivative will never be undefined, so our critical numbers are only going to correspond to the actual zeros of our derivative. And so now we just need to kind of solve this quadratic equation. And to help us solve it, we can recognize that it can be factored. Looks like there's a common factor of 4 amongst all of our terms. So let's go ahead and divide everything by 4. That allows us to rewrite the quadratic, make it easier to solve as 4 minus 8x plus 3x squared. We can now factor this using guess and check or the quadratic formula or whatever method we prefer. It's going to factor as the quantity 3x minus 2 times the quantity x minus 2, right? The product of the first terms gives us our 3x squared. The outer terms and inner terms combine to give us negative 8x. And the product of those last terms gets us back to that positive 4. So now if we actually solve for these x values, the first factor tells us x could be equal to 2/3. And the second factor tells us that x could be equal to 2. But we've already discussed what happens when x is equal to 2. That corresponds to when our volume is going to be 0. So that's not actually a critical number we are interested in, because we're trying to find a maximum, and we're pretty sure that the maximum volume of this box is going to be bigger than 0. So that just leaves us with this critical value of 2/3. We still have to verify that this critical value actually does correspond to a maximum and not some minimum or anything like that. And so to do that, we could just use our second derivative test. Right, if we take the second derivative of our volume function, then we're going to end up with negative 32 plus 24x. And if we evaluate that at 2/3, well, what do we get? We get negative 32 plus 2/3 of 24 is 16. So that evaluates to negative 16. That tells us that at this critical point, our function is concave down, so it is in fact going to correspond to a maximum. So now we've pretty much wrapped this problem up, right? We've found the x value that corresponds to the maximum value. To really finish it off, we just have to go back to that problem statement and make sure we answer the original question. And here the original question was asking for the size of the square that needs to be removed, not the actual volume or the amount of money that can be in that box or anything like that. And so the actual size of the square that needs to be removed from each corner is going to be 2/3 of a foot by 2/3 of a foot, or 8 inches by 8 inches. So we need to remove an 8 inch by 8 inch square from each corner. As long as we do that, we're building the perfect box for this situation. It will hold the most money, and we're going to be guaranteed to win that game show, assuming no one else makes the box of the exact same size.